So hello dear students, welcome to Gatewala. In this lecture we will be able to cover the first part of the continuous time Fourier series. That is a very important part, very important with respect to gate. We will be covering what is Fourier series. We will be covering the how to find out the Fourier series of some signals. Then we will be covering the properties of Fourier series. These three things we will be covering in this part. Okay. So let's start the lecture. Let's start the lecture. These all things are done, right? So now let's start the continuous time Fourier series. We have already done the LTI system property. So continuous time Fourier series. This is a method which is used to write which this is the method which is used to write or represent write or represent write or represent the periodic signals in terms of periodic signals in terms of harmonically related harmonically related complex exponentials or sinusoids. Sinusoids. So what is the meaning of harmonically related? So in periodic signals, we have one thing which is called fundamental frequency that we have already seen when I was teaching you the periodic and non-periodic signals. Okay. So if xt is having period t naught, if xt is having period t naught, and then the fundamental frequency will be 2 pi by t naught. The fundamental frequency will be 2 pi by t naught. Okay. So harmonically related complex exponential means, first of all, let us see what is complex exponential. Complex exponentials are of the format power j omega t. These are the signals which have a single frequency. These are the signals which have a single frequency. Frequency, that is omega. This signal has a single frequency, that is omega. Okay. So what is the meaning of harmonically related? So if we put in place of omega, we put k omega naught. In place of omega, we put k omega naught. Then for k equal to 1, 2, 3, 4 and for different values, we will get the complex exponentials. We will get the complex exponentials of frequency omega naught, 2 omega naught, 3 omega naught and so on. So these complex exponentials are called harmonically related complex exponentials. Okay. So for different values of k, for different values of k, and k is always an integer, right? K is always an integer. So for different values of k is always an integer. We get complex exponentials. Which have frequencies omega naught, 2 omega naught, 3 omega naught, and so on. And thus these exponentials are called harmonically related complex exponentials. Okay, so for different values of k, we get signals of frequencies omega naught, 2 omega naught, 3 omega naught, and so on. So these are the complex exponentials and they are harmonically related. Same goes with the sinusoids also. Sine of k omega naught t, cos of k omega naught t. These are also harmonically related sinusoids. These are harmonically related sinusoids. Okay, so these are the points. What is the meaning of harmonically related? Okay, so using continuous time Fourier series, we have three type of Fourier series. Okay, we have three type of Fourier series. Three type of continuous time Fourier series. The first is exponential Fourier series. Exponential Fourier series. Exponential Fourier series. So exponential Fourier series, here we represent any signal xt in terms of this complex exponentials. Okay, so this formula says that xt is equals to minus infinity to infinity summation ck e to power j omega naught kt. So it means that we are writing any signal in terms of complex exponentials, or we can say that we are writing any signals in terms of addition of the complex exponentials, and ck is the coefficient of e to power j omega naught t. ck is the coefficient of e to power j omega naught t. Okay, e to power j omega naught kt. Okay, and ck is called the exponential Fourier series coefficient of a signal. Ck is called the exponential Fourier series coefficient of a signal. Okay, always remember what is ck. Exponential Fourier series coefficient of a signal. Okay, now how to find out ck? This relationship is very important. We are writing xt in terms of complex exponentials, and ck is the exponential Fourier series coefficient. Okay, now what is how to find out ck? So ck is given by 1 upon time period. T naught is the time period of the signal, minus T naught by 2 to T naught by 2, xt e to power minus j naught kt dt. Yes. So this is the formula by which we find out ck. Okay, so ck is equals to 1 upon T naught minus T naught by 2 to T naught by 2, xt e to power minus j omega naught kt. You have to remember these two formulas. Okay, this is ck and this is xt. Now this is first category of writing, first method of writing any signal. In this first part, we are writing xt in terms of complex exponentials, as we can see here. Now the second Fourier series, that is called trigonometric Fourier series. Trigonometric Fourier series. Here we will write the signal in terms of the periodic signal in terms of sine and cosine. Okay, sine and cosine. So here the representation is xt is equal to a naught okay. So these are the two signals, these two, and this is a naught. Okay, so we can see that we are writing signal in terms of cosine harmonically related. Why they are harmonically related? We are putting n equals to 1 to infinity, and sine which are also harmonically related. Okay, so there are formulas to find out an and bn. There are formulas to find out an and bn, but generally we don't use these formulas. I'll write the formulas, but they are not used. An is equals to 2 upon time period This is the formula to find out an. And what is the formula for bn? Xt multiplied by sine n omega naught t dt. But these two formulas are generally not used, or these are not useful because generally we always find out the exponential Fourier series coefficient, that is ck, and then we convert ck into an and bn. So what is the formula? This formula can be useful. Okay, so what is the formula? The formula is an is equal to, or we can write ak also, right? We only need to change the variable. I need to change the variable here. In place of n, I'll use k because I've used k in the last slide. Too many. Summation k equal to 1 to infinity ak cos of omega naught kt, k equal to 1 to infinity bk sine of k omega naught t. Okay. Then in here also we have to change ak and bk cos of k omega naught sine of k omega naught. Okay, now okay, so we can write the ak and bk in terms of ck. You have to remember this relationship, this is very important. ak is equals to ck plus c of minus k, bk is equals to c of minus c of minus k multiplied by j. Okay, so these are the two relationships that you have to remember, ak and bk. How we can find out ak and bk from ck? Okay, ck is the exponential Fourier series coefficient that are very important to remember the formula. So these formulas you have to remember. Now third is polar form of Fourier series. After trigonometric, third is polar form of Fourier series. Polar form of Fourier series. Now what is polar form of Fourier series? Polar form of Fourier series is that polar form of Fourier series, we all know that how to write down a cos theta plus b sin theta. A cos theta plus b sin theta. How to write this a cos theta plus b sin theta? We know that a cos theta plus b sin theta can be written as under root of a square plus b square cos theta plus phi. Okay, we don't need to know what is phi. Okay, but we know that this can be written as this. So from the previous slide, if we combine these two terms, if we combine ak and bk sine and cosine terms, then we'll get this polar form. What is the polar form? Polar form is xt can be written as r naught plus under root of, or we can say r naught, a naught only, plus ak square plus bk square cos of k omega naught t plus phi k. Now phi k is not important in any sense. Phi k is not important in any sense. Summation k equal to 1 to infinity. Okay. So why this representation is very important, I'll tell you. Okay. So we can convert a sin theta plus b cos theta very easily in this form. This is polar form. Now, this representation has a very importance in GATE exam. Why? Because if in any question we have to find out the amplitude of the fifth harmonic, let us say. So then what we'll have to find? If in any question we have to find out the amplitude of the fifth harmonic. We have to find out amplitude of fifth harmonic. Then in that case, do we have to find out C5? Do we have to find out C5? Or we have to find out A5 and B5? Or we have to find out this term for k equal to 5. Always remember that anytime we have to find out amplitude of fifth harmonic, then it means that we have to find out this value at k equal to 5. We have to find out this value, that is under root of a5 square plus b5 square. We have to find out this value, always remember. So similarly, if in any case we have to find out the amplitude of the kth harmonic, then we have to find out this term. Okay, so amplitude of kth harmonic, then we have to find out, the answer is under root of ak square plus bk square. Okay, ak square plus bk square. Great. So these are the three forms in which we have to find out the Fourier series. Now before moving ahead, we will see one or two things, like how to find out the Fourier series of signals written in terms of sine and cos and complex exponentials. Okay, so before moving to properties, we will solve this. So how to find out, or before moving ahead, let's solve one question, finding out the Fourier series of a signal. So we have to find out the exponential Fourier series coefficient of signal xt. Xt is given to us. So xt is a rectangular signal like this. Suppose this is 0, center point is t naught, not by 2, by 2. This point is T naught by 4. Minus T naught by 4. Okay. Height is A. So this is the signal xt. We can see that it is a rectangular pulse which is from which has a period of T naught, and it is like this. So we have to find out the exponential Fourier series coefficient. Just recall the formula. Ck is equals to 1 upon time period integration minus T naught by 2 to T naught by 2 xt e to power minus j omega naught kt dt. Okay, omega naught is 2 pi by time period, 2 pi by T naught. Okay, 2 pi by time period. So we can easily solve it. From minus T naught by 2 to T naught by 2, this signal is capital A only from minus T naught by 4 to T naught by 4. Okay, so this is the formula now. This is the conversion. Okay, because this signal is only capital A from minus T naught by 4 to T naught by 4. Okay, this is Ck. Now we can simply solve this formula. This integration is very simple. Capital A outside divided by T naught. Then we'll integrate this minus T naught by 4 to T naught by 4. Now we'll integrate this. We'll simply put it down. Okay. Then we'll put the values. Omega naught k T naught by 4 okay. Now T naught into omega naught is 2 pi. Okay, T naught into omega naught is 2 pi. So A upon minus j 2 pi k, T will not come, T is a variable, right? 2 pi k, and here T naught into omega naught is equals to 2 pi. So this term will convert into 2 power minus j. 2 pi upon 4 is pi by 2. Now we can see that minus 2j and this term. So always remember, this is very important relationship. I hope all of you know this. Sin theta equals to e to power j theta divided by 2. Okay. So if we compare this, we can see that it is e to power minus j theta minus e to power plus j theta divided by minus 2j. Great. So this will convert into sine term. So this will become a sine of pi by 2k divided by a sine of pi by 2k divided by pi k. Okay, divided by pi k, because this minus 2j with this term will become sine theta. Okay, thus this is the Ck value. This is the exponential Fourier series coefficient. Great. So this is the exponential Fourier series coefficient. Like this, we can find out for any signal very easily by performing simple integration. Okay. Now let's move on to the questions of the format where we have to find out the exponential Fourier series coefficient of signals written in sine and cos only. So how to find the exponential Fourier series coefficient of signals written in cos or sine. So let's see the example. So first of all, let me tell you the steps. Step number 1, find the period of the signal. Find the period of the signal. So period of the signal means we know how to find out the period. If the signal is non-periodic, then obviously we cannot find the Fourier series. Okay. If the signal is non-periodic, then obviously we cannot find the exponential Fourier series coefficient because signal is not periodic, right? Second, step 2. Step 2. So from step 2 we can see that step 2 is convert using this property, sin theta is equals to e to power j theta minus e to power minus j theta upon 2j, ठीक है, and cos theta upon 2. So if we have sin theta and cos theta, we will convert them into this using the formula. We will convert all these into these exponentials. Okay. So then after converting sine and cos into these exponentials, we will have xt containing only the complex exponential terms. Xt will have containing only the complex exponential terms. Only the complex exponential terms. Okay. So I'll explain these all steps with the help of example. Now step 3 is step 3 is that now compare each term with, we'll have to compare each term with ck e to power j omega naught kt. We have to compare each term with this expression. So from here we can get k and ck. We can get k and c. Okay, so these are the steps that we'll follow, and let me tell you one example based on this steps. So xt is equals to 5 cos 2 pi t plus 7 sin 8 pi t. Let us say this is a signal. So first of all, I'll request all the students to find out that is this signal periodic, and if it is periodic, find out its period. Find out the period of the signal. So we know how to find out the period. We know that this T1 is equals to 2 pi upon omega naught, that is 1. This signal is to 2 pi upon time period, that is 1 by 4. Okay. Now we find out the ratio of T1 upon T2. We find out the ratio T1 upon T2. This will come out to be 4 upon 1. So the denominator, we have only one denominator, that is 1 only. We have only single denominator, that is value is equals to 1. So LCM of the denominator is 1. So we can say that the time period T naught is equal to T1, that is equal to 1. So we can see that omega naught is equals to 2 pi. Great. So we find out the time period and omega naught of the signal. Now what step 2 says? Step 2 says that convert these cos and sine in complex exponentials. So we'll get 5 to power j 2 pi t power minus j 2 pi t divided by 2. Great. Second, 7 e to power j 8 pi t divided by 2j. Now we'll compare all the terms of this xt with what was written. We'll compare all the terms with ck e to power j omega naught kt. We'll compare these terms with k e to power j omega naught kt. Okay. Now we'll compare these terms. If we compare the first term, what is omega naught? Omega naught is 2 pi. So let me write omega naught in place of omega naught. Let me write 2 pi only. Sorry. Okay. Now if we compare this term, the first term with that expression, so we can see that if we compare the exponential powers, so power is 2 pi t, their power is 2 pi kt. So if we compare, we can get that k equal to 1, and when we compare the coefficient, it will come out to be 5 by 2, 5 by 2. So we can get that for k equal to 1, C1 is equal to 5 by 2. Second, if we compare the exponential power, we can compare and we can get that k is equal to minus 1. Here k is equal to minus 1, k is equal to minus 1, and the coefficient is also 5 by 2, 5 by 2. Okay. So k equal to minus 1 and c of minus 1 equals to 5 by. Now here, if we compare the exponential powers, k is equal to 4 here. Okay, k is equal to 4, and the coefficient is 7 by 2j. So we can say that k is equal to 4 and c4 will be 7 by last. If we compare the exponential powers, we'll get k is equal to minus 4 and the coefficient is 7 by 2j. So this is how we can find out the exponential Fourier series coefficient of this signal. What are the coefficients? Sir, for k equal to 1, coefficient is 5 by 2, k equal to minus 1, coefficient is 5 by 2, k equal to 4, coefficient is 7 by 2j, k equal to minus 4, coefficient is minus 7 by 2j, and thus for rest of the values of k, the coefficients are 0. For rest of the values of k, the coefficients are 0. This is the way we can find out the exponential Fourier series of this kind of signal. Let me take one more example for more clarity. Okay, so let us take a signal. Okay, so this is a DC signal. It will not affect the periodicity of any signal, any part of the signal. So this is, we know that while finding the period, we can neglect this. While finding the period, we can neglect this 5. Okay. Now, the second term and the third term. The second term says that what is the period of this? Okay. So period T naught is 2 pi by omega naught. Pi by omega naught is 7 pi by 6. So this will come out to be 12 by 7. Okay, 12 by 7 is the period. T1, not T0, T1. Okay, second one, T2, 2 pi by 3 pi by 2. This will come out to be 4 by 3. Okay, this is 4 by 3 is a period. Okay, so these are the period T1 and T2. Great, great. Now we have to find out the ratio T1 upon T2, that is 12 by 7 into 4 by 3. This and this will cancel out. This will become 9 by 7. We have only one denominator, that is 7. So we can say that the LCM of the denominator is 7. LCM is 7. So we can say that T0 is equal to T0 time period is equal to LCM multiplied by T1. LCM multiplied by T1. That is 12. And thus omega naught will come out to be 2 pi by 12. That is pi by 6. Great. So now we have to convert these terms into complex exponentials, and then we have to compare all the terms to get the result. So we can write xt is equals to 5, and this 2 will cancel out because e to power j 7 pi by 6 t 7 pi by 60. Okay, this 2 will cancel out, and then this term 5 upon 2j. Okay, exponential e to power 5 by 2. Okay, now we have to compare each term with, we know the omega naught. You have to compare each term with ck e to power j. What is omega naught? Omega naught is pi by 6. Okay, so when we compare the first term, we can see that there is no exponential power. So we will get k is equal to 0 and c0 is equal to 5. Great. Understood? There is no exponential power, so means exponential power is 0. So we compare it, we get k equal to 0 and c for 0 is equals to 5. If we compare with this, we'll get k is equal to 7 and c7 is equal to 1. We compare with this, we get k is equals to -7, of -7 is equal to 1. These terms. If we compare this term with that, we'll get k value is equal to pi by 6 k is equals to 3 pi by 2. Okay, pi by 6 k is equals to 3 pi by 2. We can see that k will be equal to 9. K will be equal to 9. K is equal to 9. The coefficient C9 is equals to 5 by 2. If we compare with this, we get k is equals to -9. K of -9 is equals to -5 by 3. So these are the coefficients which will be present in this signal. Only these coefficients will be present. So Ck will have only non-zero value for these 5 values of k only. For other values of k, Ck will be 0. Great. So these are the things that we can see. Now let's move on to the properties of the Fourier series. Let's move on to the properties of Fourier series. Properties of Fourier series. These properties are very important. We'll be dealing with these properties very carefully because many a times questions are asked from these properties and directly without solving the questions we can solve the questions without any issues from the properties itself. So the first property is time reversal property. So what is time reversal property? The time reversal property says that, and first of all, let us say if we have any signal xt, we reverse the time, we reverse it the signal in time domain, then obviously the period will not change, right? If we reverse any periodic signal with respect to time, so its period will not change, the period of the signal will not change. So if xt has Fourier series coefficient ck, if xt has Fourier series coefficient ck, then x of minus t will have Fourier series coefficient c of minus k. Okay, so if we are replacing t by minus t, then we have to replace k by minus k in the expression of ck. Okay, x of minus t and xt will have same period, no doubt about it, there is no doubt on it. Okay, so these are the points. So what is the importance of this property? Importance of this property is this. Importance of the property is this. Sorry. If xt is even signal, if xt is even signal, then we know that xt is equals to x of minus t. Then we know that xt is equals to x of minus t, first point, that is the signal is even. Then using this property, we can say that ck is equals to c of minus k. That is the exponential Fourier series coefficients are also even. So if the signal is even, then exponential Fourier series coefficient will also be even. This is the first point of the, this first point for the signal is even. Now there is one more point. There is one more point here. Okay, there is one more point. Let me move on to second page for that. We have written, or we know that we know this relationship ak and bk. Ak are the coefficient of cos, bk are the coefficient of sine. Okay, we know this relationship. From here also we will get one very important relationship that you need to remember. Okay, direct questions are asked on that. So if xt is even, then ck is equal to c of minus k. Now from the formula of ak and bk, ak are the coefficient of cos, that is ck plus c of minus k. This will become 2 times of ck, because c of minus k is equals to ck itself, right? bk will come out to be coefficient of sine term. Okay, we are subtracting these two. Now since c of minus k is equals to ck, we will subtract, we will get 0. So the second important conclusion here is that if the signal is even, then if the signal is even, then sine terms are not there. Sine terms in the trigonometric Fourier series, sine terms are not there because the sine term coefficient will be 0, but only cos terms will be there. Only cosine terms are present. Only cosine terms are present. Okay, only cosine terms are present. Only cosine terms are present. Sine terms are absent. Sine terms are absent. Okay, in the even signal, only cosine terms are present. So only remember this: even signal, cosine terms. Okay, Now similarly we have for the odd signal also. From this property we can say that if xt is odd, then xt is equals to minus times of x of minus t. Xt is equals to minus times of x of minus t. So from the property we can say ck is equals to minus times of c of minus k. That is, the exponential Fourier series coefficients are also odd. Exponential Fourier series coefficients are also odd. Okay. So now from here we can get one more relationship. So we know that ak is equals to ck plus c of minus k, and when c of minus k, or we can say ck is equals to minus times of c of minus k, so we can say ak will be 0. ck will be j times of ck minus c of minus k, and here we can say minus times of c of minus k equals to ck, so this will come out to be 2j ck. So here we can say sine terms will be present, but the cosine terms will be, cos terms will be absent. Okay, cos terms will be absent when the signal is odd, Okay, so these are the two very important properties. Of the time reversal. Okay, time reversal. Next, second property, time scaling property. So time scaling property, it's a very simple property. You just have to remember this, because directly on this property one question came in 2018 of 2 marks, directly on this property. So if xt has exponential Fourier series coefficient ck, then x of at means we have done time scaling, and time scaling means obviously when we are doing time scaling, the time period will change. Okay, either we are compressing or we are expanding. In both the cases time period will change, but always remember that the Fourier series coefficient will not change. The Fourier series coefficients will not change. The Fourier series coefficients will not change. Okay, so remember that the Fourier series coefficient do not change even after doing the time scaling. But if the time period is t naught in this case, if xt was having time period t naught, x of at will have time period t naught by mod a, not by mod a. So if the fundamental frequency was omega naught, the new fundamental frequency will be equal to mod a omega naught. Only the fundamental frequency and time period will change. The Fourier series coefficient values will not change. Remember this very clearly. Okay, so this is time scaling property. Third property is time shifting property. Okay, time shifting property. So time shifting property means, so if we shift any signal, the period will change or not? Time shifting property. So if we shift the signal, the period will change or not? No, obviously not. So xt has Fourier series coefficient ck. If we do time shifting, x of t minus tau, then the Fourier series coefficient will be this. X of t minus tau will have Fourier series coefficient ck e to power minus j omega naught k tau. Remember that in time shifting, the effect goes with the same sign. Effect goes with the same sign means if we have minus tau here, then in the exponential also we will have minus tau term, minus j omega naught k tau. So we have a minus tau term. Okay. So in time shifting, effect goes with the same sign. Effect goes with the same sign. Always remember that. Effect goes with the same sign. Okay. Similarly, if we change it to x of t plus tau, then also effect will go with the same sign. We'll go with the same sign. So always remember in time shifting, and the same property will goes in Laplace also, continuous time Fourier transform, and all the transforms. The same property. Okay. So we'll continue from this point in the next session, in the next series. Okay, we'll be seeing the half wave symmetry, hidden half wave symmetry, hidden odd symmetry, and we'll be solving many questions for Fourier series. Thank you.